going to compare two other, so let's say if I gave you calcium oxide and potassium chloride, let's compare similar anions, which one would you predict has the higher entropy? This one does. Right. Okay? And if you actually go home and look up in a chart, if I was really going to make a problem, I'd want to have similar cations and similar anions. So, alrighty. Entropy, we've already talked about this one. Entropy usually increases when a pure liquid or solid dissolves in a solvent. All right, so entropy usually increases when a pure liquid or solid dissolves in a solid. I would almost say always for our purposes. You know, if you ever become a research chemist studying Gibbs free energies, then just forget I put always in here. But I would say that for the purposes of this class, when you dissolve something, that's going to be an increase in entropy. Now again, if we're going to calculate overall spontaneity, we have to take a look at what enthalpy is always telling us, but our entropy will increase when we take something and dissolve it in a solvent. And I don't know whether you expected this or not, but standard molar entropies have been calculated. And you'll notice they are all positive. That's because of the third law of thermodynamics. Because since they're state functions, we have to have some way of being able to calculate the standard, right? And so for both the enthalpy and Gibbs free energy, we assume that the elements in their standard state are 0. And then we cause reactions to occur. We calculate the change that it took to make that particular substance. Here for entropy, it's just a different way of calculating them. We assume that the perfect crystal has an entropy of 0, and they increase as the temperature rises. So you'll notice they always have a temperature. These are standard molar entropy values at 298, okay? I'm sure that if you really needed them, you could find standard enthalpy values for other temperatures. But again, being a first year class, we just kind of pick a temperature and we just use those standard entropies. So our standard entropies are always positive. We can have a decrease in entropy as we go from reactants to products. All righty. Now, if you recall, we wrote an equation that said that delta G is equal to delta H minus T delta S, correct? Now, if we're talking about a phase change, what's happening when we're changing phase? Any phase change, and this is a little phrase that is sometimes useful to have in your brain, any phase change is considered to be at equilibrium. Any phase change is considered to be at equilibrium. What did we say that the value of delta G was when we're at equilibrium? 0. And so that's where we get the delta S is equal to Q delta T. And again, we're using Q to represent heat transfer because we're really not talking about a chemical reaction. We're talking about a phase change. However, your book will use delta H in some of these places. So again, sometimes it seems like from your perspective, Q should have a specific place where you use it, and delta H should have a specific place where you use it, and so what's the deal? But they can be used interchangeably because we've assumed that the pressure is constant. Now, why do we say that any phase change is considered to be at equilibrium? If we have, say, liquid water becoming water in the gas phase. Excuse me. What's happening here, we have, during a phase change, this liquid and this gas, they stay at the same temperature, right? And what do we say is occurring during that phase change? The liquid and the gas are in equilibrium with each other. They can exist, both of them, at the same temperature. So that's why we say that any phase change is considered to be at equilibrium. Q is the heat transferred in the phase change. Our delta H is equal to 40,700 joules per mole. That would be a calculated amount. I mean, a measured amount. So our delta S is equal to our heat transferred divided by the temperature at the phase change, plus 109 joules per Kelvin mole.
Where did the 109 come from?
We took this number and divided by this
Oh,
number.
okay. I thought you were just, never mind. I thought you were also adding it. I didn't see the
Oh.
numbers.
Oh, no, that's, okay. Does that make sense?
Yeah.
Okay, yes.
Oh, where did you get the temperature?
So, the temperature where liquid goes to gas is 100 degrees Celsius, right? That's the boiling point for water. And then we have to use Kelvin, right? Because we have to agree with our entropy values. So then 100 plus 273.15, that's where we got the temperature. Remember, the temperature has to be in Kelvin, okay? All right. Do you guys want to keep going, or do you want another short break? Like just 10 minutes or so, or just stand up and, yeah. Okay, let's take another short break. Then we'll come back and we'll finish up. Yeah, let's take a short break. Thank you.
Received notice. I was just like, no, it was so stupid because like my tutor couldn't like help me out to
That the entropy will,
and he started
yeah.
talking and explaining it to me and I was like, yeah, just exhausted. Yeah, and my brain
okay.
isn't functioning right now. So I'm like, oh my god. I was doing something wrong. Which one? I could fix it. Well, we can have
So what it would really look like, probably in a way that makes the most sense, is joules per Kelvin mole.
Yeah.
And probably some